Golden Iris Productions presents a multi-scale action-structured framework relating gravitational and electromagnetic acceleration. Part 2. Based on the paper by Mark F. Dennis.
Abstract. The apparent incompatibility between quantum mechanics and general relativity has long been regarded as one of the central unresolved problems in theoretical physics. We present a structured comparative framework of three acceleration models: classical, electrogravitic, and emergent, applied across both macroscopic gravitational systems and microscopic quantum hydrogenic systems. Without simplifying or reducing structural components, each formulation is analyzed as an action-structured representation of force mediation across scale regimes. Gravitational and electromagnetic acceleration expressions are compared to identify shared structural components, including inverse power spatial dependencies, vacuum response parameters, and coupling constants associated with field interactions. Across both domains, geometric normalization factors, vacuum mediation quantities, and source-dependent coupling terms appear in structurally analogous roles. This work investigates whether these repeated correspondences suggest a deeper shared action-based framework underlying both gravitational and electromagnetic interactions. In this view, gravity and quantum electromagnetic behavior may be interpreted as scale-dependent manifestations of a common action-structured field system characterized by vacuum-mediated coupling and geometric dispersion constraints. Introduction. Modern physics is built upon two highly successful yet fundamentally distinct theoretical frameworks. General relativity describes gravitation as the curvature of space-time induced by mass energy, while quantum mechanics and quantum field theory describe electromagnetic and subatomic interactions through discrete field excitations and probabilistic dynamics. Although each framework has been experimentally validated within its respective domain, their underlying mathematical structures remain difficult to reconcile within a single unified theory. A persistent feature across both gravitational and electromagnetic systems is the emergence of inverse power spatial relationships, particularly inverse square dependence, along with the appearance of universal constants governing interaction strength and propagation through the vacuum. These recurring structures motivate comparative analysis, in which gravitational and electromagnetic acceleration laws are examined not as isolated results, but as expressions of a deeper structural framework. In this work, three distinct formulations, classical, electrogravitic, and emergent, are applied to both macroscopic gravitational systems and microscopic quantum systems. Rather than simplifying these expressions, we retain their full structural content and interpret each term as contributing to an underlying action-based mechanism. The goal is to identify structural correspondences across scale regimes and to investigate whether acceleration itself may be understood as arising from variations embedded within the equation's constituent components.
In Part 1, we developed the foundation for a unified analysis of acceleration across physical scales. We began by outlining the divide between gravitational theory and quantum mechanics, highlighting the challenge of reconciling these two frameworks within a single description of nature. From there, we identified recurring structural features common to both domains, including inverse spatial dependence, coupling constants, and vacuum response parameters. We then introduced three distinct acceleration models: classical, electrogravitic, and emergent, and applied each consistently to both macroscopic gravitational systems and microscopic quantum systems. Through direct comparison, we observed that these models share a common structural framework, with differences arising primarily from how key components are weighted across scale. This foundation sets the stage for Part 2, where these structural correspondences are interpreted in terms of a deeper, action-based and vacuum-driven mechanism underlying acceleration.
Classical model comparison. The macroscopic classical gravitational acceleration is given by A macro classical equals gm over r squared, while the microscopic classical electromagnetic acceleration is A micro classical equals kq squared over MEA0 squared. Both expressions exhibit inverse square dependence, though applied to different spatial parameters. In the macroscopic case, the dependence on r squared reflects geometric dispersion over physical distance, whereas in the microscopic case, A0 squared represents a fixed confinement scale associated with the bound state. The coupling terms differ in nature: gravitational coupling through Gm and electromagnetic coupling through kq squared, while the microscopic expression introduces an explicit inertial term Me, reflecting inertial resistance within the bound system. Structurally, both equations take the form of coupling strength divided by a spatial scale squared, indicating a shared action-based dependence on interaction strength and geometric or confinement scaling. In this comparison, the gravitational coupling term G is structurally replaced by the Coulomb coupling constant K, while the source term M is replaced by the charge interaction term Q squared. The introduction of the electron mass ME in the denominator provides an inertial balance against the comparatively strong electromagnetic coupling, stabilizing the bound state system. While the macroscopic equation describes free field geometric dispersion, the microscopic equation incorporates both coupling and resistance within a confined spatial scale. Despite these differences, both expressions retain the same fundamental structure, a coupling term governing interaction strength distributed over a squared spatial parameter, indicating a shared action-based dependence across regimes. Electrogravitic model comparison. Here, the core vacuum response structure is identical in both expressions, consisting of the radial dependence 1 over 2r, the vacuum parameters epsilon naught and u naught, and the deviation term 1 over epsilon naught over epsilon local. The microscopic expression introduces an additional multiplicative factor, proportional to 1 over r squared, resulting in an effective higher-order radial dependence. This additional scaling reflects the increased strength and localization of field gradients in the quantum regime. The comparison demonstrates that the electrogravitic model preserves a common kernel across scales, while modifying its spatial dependence to account for confinement and intensity differences. Both expressions share an identical vacuum response kernel, indicating that the same underlying structure governs acceleration in both domains. The additional factor of 1.99964 over r squared in the microscopic expression introduces a scaling consistent with stronger, more localized field gradients. Notably, the numerical factor 1.99964
closely approximates the value of 2, which appears frequently in both quantum and relativistic contexts, such as in expressions involving gravitational potential corrections, e.g. 2gm over r. Within this framework, this factor can be interpreted as a scaling coefficient, linking quantum-level confinement behavior to relativistic and gravitational boundary conditions. The result is an amplification of the same vacuum-mediated structure observed in the macroscopic case, rather than the introduction of a fundamentally different mechanism.
A more detailed examination of the interaction between the macroscopic normalization factor and the quantum scaling term reveals an additional structural correspondence. The radial component of the electrogravitic kernel contains a factor of 1 over 2r, while the quantum correction introduces a multiplicative factor of 1.99964 over r squared. When considered together, these combine to form 1.99964 over 2r cubed, in which the numerical factor 1.99964 effectively compensates for the factor of 2 present in the denominator. Since 1.99964 is approximately 2, their ratio approaches unity, yielding an effective radial dependence proportional to 1 over r cubed, without altering the underlying vacuum response structure. Within this interpretation, the factor of 2 in the macroscopic expression can be viewed as a geometric or normalization term associated with large-scale boundary conditions, while the quantum scaling factor restores this normalization at small scales. The result is a transition from a distributed 1 over r behavior in the macroscopic regime to a highly localized 1 over r cubed behavior in the microscopic regime. This transition does not introduce a new interaction, but instead reflects a scale-dependent rebalancing of existing terms, reinforcing the view that both regimes are governed by the same underlying action-structured system.
The electromagnetic field exhibits a significantly steeper spatial gradient than the gravitational field, due to both its stronger coupling and its confinement to much smaller spatial scales. Within the present framework, this difference is further reflected in the transition from a distributed 1 over r dependence to a localized 1 over r cubed dependence, indicating that the increased strength of the quantum field corresponds to a steepening of the underlying energy-time gradient rather than a fundamentally different interaction. While classical gravitational acceleration follows an inverse square dependence, higher-order terms proportional to 1 over r cubed arise in relativistic treatments governing orbital stability and strong field behavior. Notably, the photon sphere of a Schwarzschild black hole occurs at r equals 3 gm over c squared, marking a regime where curvature effects dominate. The appearance of similar 1 over r cubed type scaling in the microscopic electrogravitic formulation suggests that strongly localized quantum systems and strong gravitational fields may share a common underlying gradient structure.
The macroscopic emergent acceleration and the microscopic emergent acceleration expressions contain geometric normalization through the factor 4 pi, though appearing in reciprocal positions. Each also includes vacuum mediation via epsilon naught and spatial scaling through squared distance terms, r squared in the macroscopic case and a naught squared in the microscopic case. The macroscopic expression incorporates Planck scale structure through Lp squared and an effective mass-energy term me, while the microscopic expression includes the electron mass me as an inertial parameter. Notably, the role of the charge term q squared appears inverted between the two expressions, suggesting a redistribution of coupling significance between scales. Despite these differences, both equations maintain a consistent structure of geometric normalization, vacuum mediation, and a ratio between coupling and resistance terms.
From this perspective, the emergent formulation suggests that what appears as a weak gravitational coupling at large scales may correspond to a scaled-down manifestation of more fundamental interactions, while the strong electromagnetic coupling at small scales represents the inverse scaling of these same structural components. In this sense, the macroscopic expression may be viewed as a projection of large-scale behavior derived from small-scale structure, while the microscopic expression represents the localized high-intensity limit of the same underlying system. In the transition from the macroscopic to the microscopic formulation, the Planck scale components Lp squared and alpha, along with the vacuum propagation term 1/u0, are effectively absorbed into the definition of the bound state system. At quantum scales, these parameters no longer appear explicitly, because their influence is encoded within the Bohr radius A0, which defines the characteristic spatial confinement of the electron. In this sense, A0 squared replaces R squared as a fixed geometric scale, representing a localized equilibrium condition in which Planck scale and vacuum structure effects are implicitly embedded rather than independently expressed.
This reflects a shift from an explicit, distributed representation of fundamental constants at macroscopic scales to an implicit, normalized representation at microscopic scales, where the same underlying structures are contained within stable quantum parameters. As a result, the microscopic emergent equation can be interpreted as a compressed form of macroscopic expression, in which foundational constants are absorbed within measurable quantum scales, rather than appearing as separate factors. While the electromagnetic interaction is significantly stronger than gravity at quantum scales and therefore dominates the dynamics of the system, the absence of explicit Planck scale and vacuum propagation terms in the microscopic emergent formulation arises primarily from the formation of a bound state equilibrium. In this regime, fundamental constants that appear explicitly at macroscopic scales become embedded within the Bohr radius A0, which serves as a fixed geometric scale encoding the underlying vacuum and coupling structure.
In Part 2, we moved beyond structural comparison and into interpretation. We examined how the repeated patterns across classical, electrogravitic, and emergent formulations point toward a common underlying mechanism. Rather than treating acceleration as the result of distinct forces, we explored the idea that it arises from structured variations within the vacuum itself. By analyzing both macroscopic gravitational systems and microscopic quantum systems, we saw that differences in behavior can be understood as scale-dependent expressions of the same foundational components. In this view, coupling strength, spatial scaling, and vacuum response are not independent features, but interconnected elements of a single action-based framework. This perspective suggests that what we observe as gravitational and electromagnetic acceleration may reflect a deeper geometric and temporal structure embedded within the vacuum. In Part 3, we will extend this interpretation further, exploring the implications for motion, inertia, and the nature of space-time itself. To be continued.